Hello everyone. So today's topic is very important and very interesting. Archimedean property. The Archimedean property, this is the statement of this property is as simple as fresh water, but this property is widely applicable in mathematics. So what is the property? Suppose we have two positive real numbers A and B. A and B, these are two positive real numbers. Okay, then Archimedean property says that there exists a natural number n belongs to set of natural number such that na that will be greater than b. So we have two positive real numbers A and B. Then there exists a natural number n such that na will be greater than b. So what is the statement? Statement. If A and B be any two positive real numbers, then there exists a natural number n such that na that will be greater than b. Okay, so the statement is very simple, but the application of this property is everywhere in mathematics. So let's see the proof of this statement. Proof. So I will prove this theorem in contradiction method. So without loss of generality, let us consider that NA, this is less than equals to B. The contradict statement of NA greater than B, this is NA less than equals to B, where A and B, those are positive real numbers and N belongs to set of natural number. Okay. Now, if we consider that the set S, I am considering a set S. Okay. S is equals to NA such that N belongs to set of natural number. Now, since NA is less than equals to B, then we can say that this set S, this will be bounded above. Okay, and the B is our upper bound. B is upper bound. I am repeating, since NA less than equals to B, so I form a set S where the elements are in this form NA. Since NA is less than equals to B, so we can say that the set S that will be bounded above, and since it is less than equals to B, that means B is an upper bound. Okay, now since the set S is bounded above, then by the completeness property of the ordered field, by completeness property of the ordered field, what we can say by this property, we can say that the set S, this set must have a supremum. S must have a supremum. Okay, now I am considering that let capital M is equals to supremum of S. So by completeness property, S must have a supremum, and I am considering that capital M is the supremum of S. So we can say that since M is supremum, so we can say that NA that will be less than equals to M, right? Now, what I am doing? n plus 1 into a. Okay, that will be again less than equals to m, right? This is n natural number. I am taking the next natural number n plus 1, and this will be again less than equals to m. So if I simplify it, this is na plus a, this is less than equals to m, or na less than equals to m minus a. So here na less than equals to m, and here na less than equals to m minus a. That means m minus a, this is again an upper bound. Again an upper bound. But we have considered that m is supremum. That means least upper bound. So we are getting an upper bound m minus a, which is less than m. That means m cannot be supremum. M is not supremum. So here is a contradiction. We have assumed that m is supremum, but here I am getting that m is not supremum. So here is the contradiction. So our assumption that NA, this is less than equals to B, this assumption is totally wrong. So we can say that NA, this is greater than B. And this is the statement of Archimedean property. Okay. Now, using this Archimedean property, we have some corollary. What are those corollary? Corollary 1. Corollary 1. In Archimedean property, we have considered that A, B, those are positive real numbers, and n belongs to set of natural number. Now in corollary 1, I am considering that A is positive real numbers, but B is arbitrary. B is arbitrary. Then what will be the result in this case? Again, this will be NA greater than B. Okay. Now corollary 2. Corollary 2 is for any positive real number, A belongs to R plus, positive real numbers. There exists N belongs to set of natural number such that N is greater than A. For any positive real number A, you will get a natural number N such that N is greater than A. For example, suppose I am considering A is equals to 27.5. Okay, then you can find a natural number N is equals to 28, where this A is less than N. Okay, and you can choose any natural number which is greater than this 27.5. Okay, so this is the corollary of the Archimedean property. Now corollary 3. Corollary 3 is here A, this is positive real number. Now what will be if I choose A is arbitrary? That means A is arbitrary. And N from natural number, again the relation will hold. That is N will be greater than A. So if A is positive real number, so in that case, you can find a natural number where N will be, the natural number will be greater than the positive real number. And similarly, in corollary 3, I am saying that if A is any arbitrary real number, then again you can find a natural number N such that the natural number will be greater than the arbitrary real number. Okay, so this is the 3 corollary of Archimedean property. So in this video, I have discussed the statement of Archimedean property. I have proved the Archimedean property, and I have discussed some corollary of this property. I think this video will be very helpful and beneficial for you. If you are satisfied, then share it with your friends and subscribe our channel. Thank you.